So hello and welcome back. Today is lecture 7-1B on Bayes filters, extended Kalman filters, in particular how we use them for localization. Kalman filters, recall, are parametric and work on continuous state space instead of unlike discrete or particle filters. So assume that they are linear, which is what we use for Kalman filters, so they can be used to solve problems by using recursion. Well, today we're going to examine what if you have nonlinear properties like most mobile robotic systems do. Then we can do something that we call an extended Kalman filter, which is primarily applied to feature-based maps. The maximum likelihood technique is used to deal with the correspondence problem, and this approach assumes at each point in time the most likely correspondence is correct. And there's also multi-hypothesis tracking that pursues multiple correct correspondences using a Gaussian mixture to represent the posterior. We will not discuss in detail the multiple hypothesis tracking because we will focus today's lecture on the extended Kalman filter. So recall that our Bayes filter and model had a prediction and a correction. The prediction was based upon the motion model, and it's the approximation of the belief given the integral over the previous states, the probability of a certain state given the previous state, and the input, which is the motion, times the previous belief, and you take the derivative of that over the state. The correction model is based upon the sensor model, where you correct that belief by multiplying by the normalization constant times the probability of a given sensor knowing the state times the approximate belief. So we can now say that our Kalman filter is a special case of a Bayes filter. However, in Kalman filters, the equations are only applicable to linear systems, as we saw in the previous lecture. So most realistic robotic problems involve nonlinear functions. So instead of having that linear combination of the matrices and the inputs and the states, you would have something more like this, where x is a function of u and x of t minus 1, and the sensor model is a function of xt. So what our job is to try to linearize these by using Taylor expansion. So here's an example, again, of what this looks like. If you have a Gaussian function in the linear world, and you have the advantage of being able to use a Kalman filter, and then you map it through a linear function, y equals ax plus b. We saw this in the previous lecture. Then the output will end up being a Gaussian as well, but with a new mean, as well as a new standard deviation. So you're able to send in a Gaussian, map by a linear function, and the output will be a Gaussian. And so it's the Bayes filter in a closed form. So this is the ideal solution when you have a Kalman filter. But what happens when you cannot map it through a linear function as shown here? So we now have this nonlinear function and this g of x, and now when we map, the output is no longer a Gaussian function. So what we see here is the output is p of y, and then we have the Gaussian of p of y, where we basically find the mean over all values, and we plot that, and then we find that mean. But we see that p of y in and of itself is not a Gaussian function because we had to map through that nonlinear function. So what is the solution to that problem? So the solution to this problem, so that we can apply a Kalman filter, is to do something that we call local linearization. So this means we're going to use a Jacobian in order to do a local linearization, and then we can now apply our Kalman filter to this nonlinear approach. So what happens is now our prediction and our correction models are going to have this Jacobian model as shown here, where it's the partial derivative of g with respect to x to get the G matrix, which is a Jacobian matrix, or the partial derivative of h with respect to x. And by using that, we also get another Jacobian matrix. So now we can approximate that function g of ux or h of x as now a linear combination of two matrices where times x minus u or times u, where now one of our inputs is actually the Jacobian matrix. So recall that the Jacobian matrix is a non-square n by m matrix in general. When you give a vector valued function that is nonlinear, f of x equals f1 of x and so on, then the Jacobian is defined as the partial of f1 with respect to x1, the partial of f1 with respect to x2, and so on as shown here. Another way to think about the Jacobian matrix is it's the orientation of the tangent plane to a vector valued function at a given point, or like the slope of the tangent at that point, which in our case is going to be mu, or you can generalize the gradient of a scalar valued function in 3D as shown here on the right. So the extended common filter linearization using a first order Taylor series expansion is shown here, where the prediction function becomes g of ux is approximately g of u t minus 1 plus the partial derivative of g with respect to x times xt minus 1 minus ut minus 1, or written in terms of our Jacobian matrices, it would be gu ut minus 1 plus now gt and ht are no longer nonlinear because they are approximated by linear functions, and the benefit of using these is we can now use our common filter because we now have a linear approximation of the prediction and the correction model. And so now this is what it looks like when we use Taylor expansions in order to map from our input Gaussian to our output. And so what you see here is that at the output, the blue line represents the Gaussian of P of Y, where you find the mean and the variance to plot that one. And not too different is actually the one you found by linearizing your function g of x. And we now see that that red line would represent the extended common filter Gaussian output. And so that approximation is not too significantly off from the one you got by finding the mean over P of Y. Now, the question becomes, how does this change as the variance in the input Gaussian changes? So as you can imagine, as the variance becomes larger, the approximation for the Taylor expansion or Jacobian becomes a little bit worse. So here's an example of that. So now what you see is that the input Gaussian has a bigger variance. We use the same linearization technique, but now you notice that there's a larger error between the Gaussian of P of Y and the extended common filter of the Gaussian, where they don't match quite as well because there's a larger sources of error as it varies more away from the linearization point which we found at the mean. But then conversely, what you would find is that you have a more narrow Gaussian or less variation, and then we do the linearization at that mean. Then we see that the Gaussian of P of Y and the extended common filter of that Gaussian are almost identical. So what you can say here is that very low approximation error is because of the lower uncertainty in the input Gaussian, and that also lowers the effect of the linearization due to the lack of a lot of variation in the input. So here's the algorithm that we now use for our extended common filter. And what you should observe here is that there's really not a big difference between this algorithm and the one we had in the previous lecture. The main difference is we have to substitute in our linearized matrices. So for example, where we had mu is g of ut minus 1, we now can replace that with ut equals a, ut minus 1 plus bt ut. And sigma would be g2t sigma t minus 1 gt plus rt, where we now can replace our A matrices that we had before with our G matrix. And that is our Jacobian matrix for linearizing that function. And similarly for the correction, same, where we're going to have sigma h times h sigma bar h plus qt inverse, where we now have replaced the h, which is our Jacobian linearized matrix. We replace h with the c that we had originally before. So the key difference between what we had before and here is you just replace those linear functions or linear matrices we had before now with our linearized matrices. And then other than that, you go through the same algorithm in order to output mu and sigma. So here's an example of that. from RoboCup, once again, where we have the Sony Aibo dogs that have a camera in them, and they're able to do extended common filter localization by looking for point features such as the color signature on the towers in the arena, and they're able to estimate the angle and distance from these visual landmarks of where the robot is located based upon the size of the landmark in the camera as well as the displacement in the middle of where that landmark is. So once again, the extended common filter localization using the Jacobian with respect to the location, which is going to be mu, you can find GT, you can find VT, or our velocity model, and now we have our motion model where we can estimate our linear velocity, our angular velocity, and our noise by using the linearization of this data. And then you can find a predicted mean mu and the predicted covariance sigma. So that would be our prediction. And then for our correction, you can have a prediction of the measurement mean, and you can find the Jacobian of that value with respect to h by doing the partial derivative again. And then you can find the simulation of that noise error Q. And then we can predict the measurement covariance by using S equals H sigma H transpose plus Q. And the Kalman gain would be sigma H transpose times S inverse. And we now can get an updated mean and an updated covariance to correct our prediction based upon our sensor model. And then here's what it looks like when you put this information together. So if it is your prediction step, which means we're looking at the motion model and we send in a motion input, we can now look at how you sum VT M2 VT and GT sigma T minus 1 GT. And based upon different noise models, then gives you an estimate of where the robot would be after it implements that motion step, where you're also going to be looking at the sources of error and the probability that it's there. So notice as the noise model becomes larger, then you have a larger variation of where the robot's final location would be. And here's an example of the observation prediction step, where now you have that sensor input and you're using that to estimate the robot's location. But once again, we're looking at how does this model change as the various uncertainties from the predictions change. And you notice that it not only changes where the robot's final location is, but also the prediction error in it being in that spot. So then here's our correction spot again, where we now have the output of our Kalman filter, where we're taking our inputs, which are our motion model on the left, and then we're looking at our sensor model on the right. And then when you put both of those together, this is giving you estimates of where the robot has localized based upon the prediction and the correction step. So once again, the estimation sequence would start with the ground truth on the left with the robot, as well as the dashed lines, which indicate how the robot's moving, and the information on the robot and sensor data as it's moving around. And then we have this model on the left, which is the solid line of the extended common filter with its uncertainties, which represents the robot's possible location as it moves through the world. And here's another example where you model the uncertainties differently, where once again on the left we have the ground truth of the robot with respect to the motion model and the sensor model. And then on the right, you have the solid line, which represents the output of the extended common filter, along with the certainty or uncertainty that the robot is at each of those locations. And finally, this concludes our summary of the extended common filter. So some of the key points is that this is an ad hoc solution in order to deal with the non-linearities, where we use the Jacobian in order to find the Taylor series expansion around some point. We perform this local linearization in each step, and now we're able to use this with our common filter that we developed in the previous lecture, and it does work well in practice for moderate non-linearities, but notice that it does diverge if the non-linearities get too large, and if that's the case, you're probably better off to use a different type of localization algorithm, such as the discrete or particle filters. But this does work well for landmark localization, although it may not be optimal. And even when some of the assumptions are violated, you may still be able to find that you can use EKF for localization. Thank you for coming. Thank you for listening, and have a great day.